Have you ever wondered why people do research? One obvious answer to this is to have an impact, being scientific, industrial, or societal impact. Talking about these impacts, the United Nations has defined 17 Sustainable Development Goals as a roadmap for creating a better, healthier, more sustainable, and more prosperous world. These ambitious goals, however, cannot be achieved without the help of science and technology, among many other things, of course. We at our research group address a number of these goals, namely related to Goal 3, Good Health and Well-being, Goal 9, Industry, Innovation and Infrastructure, Goal 11, Sustainable Cities and Communities, Goal 13, Climate Action, and Goal 15, Life on Land. If you wonder how we address these challenges, our research is focused on interconnected, resource-aware intelligence systems. In this context, we design, analyze, develop, and evaluate concepts, models, algorithms, protocols, and tools to optimize performance of distributed networked embedded systems. If this already sounds good to you, you may be interested in one of our 3 research lines: Pervasive Networking, Pervasive Computing, and Predictable Performance. I now give the word to my colleagues to explain what can be expected from each of these 3 research lines.
It has been many years since the introduction of Wi-Fi, and we still have problems with it. And the typical setting for that is just one laptop connected to an access point. Now, let's make this a bit more interesting. What about networked applications that are parts of our daily lives and physical environments? Think about a campus-wide parking application, which runs on many resource-poor devices on top of all sorts of heterogeneous networks. Perhaps a server is needed to collect all this information and coordinate parking. We need a billing service that keeps track of payment data and manages access accordingly. It gets very complex very fast. In the Internet of Things, we are talking about such applications that go beyond pure digital. The pervasive networking research in our group is fueled by the communication needs of such applications built on top of resource-poor embedded devices. For example, think about devices that are connected via Zigbee, Bluetooth, millimeter wave, 5G, LoRa, and more. A lot of these devices want to sleep 99% of the time to get by on battery power for years. And on the other hand, they must be reachable by other devices on the internet. There is one constant: information flow across different networks of sensors and actuators through multiple communication protocols is a must for correct operation. As a result, communication and semantic interoperability across different types of networks and devices becomes a key challenge. Here, semantic interoperability refers to the ability to interpret information exchanged with the same meaning. So, when a thermometer measures that the temperature value is 20 and sends this value to a thermostat, there should be no ambiguity at the receiving side about whether this refers to 20 Celsius degrees or 20 Fahrenheit degrees. The whole application, in this case of temperature control, depends on this. We envision a future of intelligent IoT systems where anyone can just buy an IoT-enabled device from a shop, power it up in their living room, and watch it automatically join other IoT devices to take part in some task of the user in an adequate way for a long time. In our research, we strive to fill the gap between this vision and the state of the art. An example of the practical impact of our research was the development of the first Philips Hue network architecture in a student assignment, which made it into the product line of Philips a couple of years later, turning out to be a huge success story with millions of units sold worldwide.
Computers are all around us. Our laptops, smartphones, wearable devices, all kinds of sensors. Now all of those devices, they generate data. And that data must be stored, communicated, processed, and analyzed. Tanner just told you about the challenges in communicating the data. Let me tell you about some of the challenges in processing and analyzing it. Many of these computing devices must be small and cheap so that they can be embedded in our surrounding. They often run on batteries, have little memory and processing power. Computing on these devices is really tough. So the challenge is, how do we process all of the data these devices generate? Can some of the processing be offloaded to larger and less constrained devices or the cloud? What do we process locally and what do we communicate? With these many devices around us, some of them will fail or simply run out of battery. How do we make decisions when the data we need is incomplete? With the devices continuously on and monitoring our every move, how do we preserve privacy while providing these data-driven services? Many modern state-of-the-art machine learning algorithms are validated on clean synthetic data. Unfortunately, real data hardly ever is complete and clean. For example, if you go to a high-tech manufacturing company and your task is to predict when a machine will fail based on the data from several sources, you may expect to see data like this. But in reality, you will see something more similar to this. The problem is that some sensors will fail or will be misconfigured. The data will contain gaps or corrupted values. So, how can we complete the machine learning tasks such as failure prediction in spite of such noisy data? How can we observe that the sensors have failed, and how can we identify other data sources to replace them? How can we rely on expert knowledge of operators and process engineers to make these models more resilient? Within our group, we aim to address these challenges with methods from domains like edge computing, federated learning, reliable machine learning, and self-learning systems.
Today, systems are expected to become smarter, more autonomous, flexible, and adaptable. Let's take the example of your car. 25 years ago, it barely contained any electronic, a couple of computers, and a few sensors. Today, software of a modern car is made of millions of lines of code executed on hundreds of embedded computers. As rightly stated by Mike, all those sensors and computers produce and treat data. Tanir and Mike already discussed about challenges with respect to communicating, interpreting, processing, and analyzing those data. But there is another aspect that is most often overlooked when designing such systems: predictability. Most functionalities have timing constraints associated with them. To illustrate this, let's come back to our example of our car. And let's consider a situation where the driver assistance system must react to a dangerous situation and activate the braking system to avoid a collision. To achieve this, several sensors must produce data. Those data must be communicated to computers, potentially on the other side of the car. The data must then be treated to decide the appropriate action to take. That action must then be communicated back to the braking system, where it can finally be implemented. Now, all these communications and task executions take time. Yet, the time between the detection of an obstacle on the road and the activation of the brakes must be predictable. What would be the use of the brakes activating even a second after the dangerous situation has passed? The example I just gave is rather obvious, of course, but the same applies to any functionality that is meant to inform, control, or make any type of decisions. All of them must meet timing and quality of service requirements. So, how can you analyze the communication delay between the different sensors, computers, and actuators involved in these complex tasks? How can you predict the response time between the sensing and the actuation events? How can you configure the system to guarantee that timing and quality of service requirements are respected for all the applications that concurrently execute in the system? What mechanisms can you implement in an operating system, in a switch, or in an FPGA to improve the time determinism of your application? Within our group, we develop tools to model, analyze, and configure modern cyber-physical systems so as to ensure predictable performance. We design and integrate new features in the next generation of operating systems, Ethernet switches, and integrated circuits to improve the predictability of the applications that we run on top of them.
Do you also wonder what kind of job market awaits you after finishing your research at our group? Our previous graduates have found jobs at companies such as NXP, ASML, Signify, Philips, Google, Amazon, ING Bank, Bosch, and many other companies and universities. Through training professionals and close collaboration with our industry and academic network, we also work towards the final United Nations Sustainable Development Goal, namely Goal 17, partnership to achieve the goal. Now, if you are ready for an amazing challenge and want to contribute to create a better world with the help of your research results, please join us. On this link, you'll find a list of our available assignments. If you don't find your dream assignment there, please contact us, and we together will make your dream come true.